did I not? I posted it long. Oh, what is this stuff? Yeah. They should be coming in now. So. Okay, good morning, guys. First things first, I just noticed that I have not yet published your study guides. And I'm sorry for that. It just slipped my mind. I've been very busy. So I'll get those done immediately after class today. I'll get those posted up for you. They'll be short. But today we have a few new things to talk about. Let me get the doc cam fired up. Swap over that. Oh, what do you mean it's not connected? All right. This is MAC2312.001. And today is the 28th. So first thing, yeah, study guide 2 will be up right after class. So I'm sorry about the delay there. That was definitely my fault. Busy grading exams for another class and it just slipped my mind. But today we're going to learn our last 2 convergence tests. We're going to learn about the root and ratio tests. And this concept of absolute convergence. And this is section 11.6 in the textbook. The camera doesn't seem to want to focus on that blue pen, so I'm going to switch to another color here, but I'm running out of bold colors. Okay. Let's see now. So we can talk about the tests, but really we should talk about absolute convergence before either of the tests. So you remember on Monday, we learned about alternating series, and those are the first series that we've messed with where some of the terms were negative and some of the terms were positive. In previous sections, every series test you have, like the comparison tests, the integral test, all that stuff, required that the series have only positive terms, with the exception of telescoping and geometric series, which are special. The root and ratio tests can also be applied to series in which not all the terms are positive. But when we talked about alternating series, we noted that the series where you add, subtract, add, subtract, add, subtract, the alternating series have an easier time converging, right? Like for example, the alternating harmonic series converged even though the regular harmonic series diverged. There's a special name for that sort of convergence, where the version that flips back and forth in sign converges, but the version that doesn't flip back and forth in sign diverges. And to talk about those, we need to talk about absolute convergence. So if sigma n from 1 or wherever to infinity, the absolute value of an converges, then we say that the series without the absolute values converges absolutely. Of course, if the ANs are all positive, then this series is the same as this series. So every convergent series with only positive terms is absolutely convergent. But the thing is interesting when you start looking at alternating series and you ask, well, if I take away the alternatingness by slapping on some absolute values, does that hurt the series enough to keep it from converging, whereas it did converge before? We can go on a little further here to say series which converge but have the absolute value version diverging are called conditionally convergent. So these are kind of the two new terms that we need in order to start talking about the material in this section. Absolutely convergent means when I slap on some absolute values, you stay convergent. Conditionally convergent means when I slap on some absolute values, you go from convergent to divergent. Some examples. This series is absolutely convergent. Because if I take absolute values inside, I get a convergent p-series. So this series, this is an alternating series, right? The negative 1 to the n. My bn's here are 1 over n squared. But if you take the absolute value inside the series, then you get a normal p-series. And this normal p-series is convergent because p here is equal to 2, which is bigger than 1. So it satisfies the definition, right? The series here is a series who, when I take absolute value inside, the result is a convergent series. Any convergent series with positive terms is absolutely convergent. Because if AN is positive, then the absolute value of AN is just AN. So the absolute value series is the same as the original series. So if you have a convergent series in which all the terms are positive, that's automatically absolutely convergent. The series that we were playing with last time, this guy is conditionally convergent. Because this series converges by AST. We did this last time. But if you take absolute values inside, then you get a P series with P equal to 1. Because the absolute value of -1 to the n plus 1, that's just 1. And the absolute value of n is just n. This is a divergent series. Okay. So a few examples of absolutely convergent series and conditionally convergent series. A handful of problems in your homework this week ask you to classify series as absolutely convergent, conditionally convergent, and divergent. Every series lands in one of those boxes, and there is no overlap between those boxes. So every series is either conditionally convergent, absolutely convergent, or divergent. Questions on the definition or any of these examples here? Absolute convergence turns out to be kind of the nice restriction to put on your series if you want to start messing around with them. Conditionally convergent series are very weird. I can take a conditionally convergent series and reorder the terms so that it diverges. I know that sounds fucking strange, but it's true. If you take, for example, the alternating harmonic series and you put all the odd terms together and all the even terms together, both of those on their own diverge. Strange, right? But somehow when you put them together, they converge. Or if you take a telescoping series like 1 over n minus 1 over n plus 1, and you split that up into sigma 1 over n minus sigma 1 over n plus 1, both of those diverge. So there's something very special about absolute convergence, and there's something very weird about conditional convergence. And for our level right now, the most important thing to remember is that absolute convergence is much stronger. If you have a series that's absolutely convergent, then you can be 100% certain that no matter what you do to that series, it will stay convergent and it will keep the same value. You can split it up, you can set it on fire, You can differentiate it. You can do all sorts of weird shit, and the series will remain convergent. Whereas with conditionally convergent series, you start splitting them up or setting them on fire or differentiating them, they can fall apart. In fact, there's a theorem that's a little bit too deep for this class, just a smidge too deep, called the derangement theorem, or sometimes called Riemann's derangement theorem, that says if you give me a conditionally convergent series, I can fuck with the order of the terms to make it converge to a different number. Weird, very weird. So when I say absolute convergence is stronger than conditional convergence, in at least one sense, I can make that very concrete. If sigma an converges absolutely, then sigma an converges in the normal sense. In other words, every absolutely convergent series is convergent in the traditional way. And this is a consequence of what we call the triangle inequality in mathematics. The triangle inequality you may have heard of in different language. It says that the shortest way to get from one point to another is a straight line. In other words, says that the absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. If you think about this for a minute, it makes good sense. Try plugging in some numbers for x and y. If x and y have the same sign, both negative or both positive, then the left-hand side is equal to the right-hand side. But if x and y have opposite signs, one is positive and one is negative, then the left-hand side will be strictly smaller than the right-hand side. Because here you're going one way with one of them and the other way with the other. If x and y have opposite signs, say x is positive, he walks you to the right, and y is negative, he will walk you back to the left. So this will end up being smaller than if you walk to the right that same amount in both cases. This can be extended to the triangle inequality for n terms. I'll write it with a capital N here, why not? That way we can see the connection to partial sums. The trick to extending from the two-term triangle inequality to the n-term triangle inequality is to use what's called mathematical induction. Some pre-calculus classes discuss mathematical induction, some do not. I think probably most do not. Or if they do, it's probably discussed in a way that makes it feel magical and weird. But you know, what works for 2 works for 3. What works for 3 works for 4. What works for 4 works for 5. What works for 2 generally works for arbitrarily finitely many. And of course, on the left-hand side here, you have the partial sum with absolute values outside. This is this. And what you have on the right-hand side is the partial sum with absolute value inside. So I want to be clear, taking absolute values outside is not the same as taking absolute values inside. When we talk about absolute convergence, we're talking about doing this, taking absolute values on the inside. So don't tell me that these things are equal. You want to be very careful in your writing to make sure you don't conflate these. But what is true is this inequality. And sending n to infinity we get this. So if the object on the right here is finite, that is the series sigma an converges absolutely, then the object on the left is finite. So if this series is finite, which is the same thing as saying the original series converges absolutely, then sigma 1 to infinity an, all in absolute values, must be finite because it's smaller than that. Hence, now what sort of things have finite absolute value? Just finite things. And that's the proof. If you converge absolutely, then you converge. So absolute convergence is strictly stronger, right? Every absolutely convergent series is convergent in the traditional way, but the converse is not true. We've seen that there are series that converge, but fail to converge absolutely. The alternating harmonic series is a classic example of this. Another example coming from your homework God damn it. Is to classify some series that look like this as conditionally convergent, absolutely convergent, or divergent. Does anybody have an idea as to how you could get started on this? Yeah, certainly. I'd like to start out. Yeah, okay. So Juan and Maggie both have a good idea here. We can take the absolute value of the series on the inside and see whether or not that converges. And we can investigate the convergence of the series as it was given to us. Now, as it was given, it's an alternating series. So I would begin with the alternating series test. Here the bn's are 1 over the natural log of n. And the bn's are decreasing. Because the natural log of n is increasing. Picture the graph of the natural log, it's always going uphill. And the limit of the bn's is the limit as n goes to infinity of 1 over the natural log of n. And the natural log limit is one we've talked about a bunch. As n goes to infinity, the natural log of n goes to infinity. So this is 1 over infinity, which is indeed 0. Hence, the series S converges by the alternating series test. Okay, so the series is convergent. But is it absolutely convergent or conditionally convergent? It's got to be one of those two. Can't converge and not fall into one of those boxes. So which box does it fall into? That's the question. We know it doesn't diverge. We know that the series converges because it passes AST. To answer the lingering question, is the convergence absolute or not? We look at the related series. Now we have to take the absolute value of everything inside. We can't take absolute values of just one piece. But the absolute value function plays very nice with multiplication and division. This is the same as the sum from 2 to infinity, the absolute value of -1 to the n over the natural log of n in absolute values. And since n is starting at 2, the natural log is positive. Right? The natural log goes from negative to positive at 1. So the absolute value of the bottom is just the bottom. What about the top? What is the absolute value of -1 to the n? Yeah, it's just 1. This piece, the -1 to the n piece, is either 1 or -1. And when you take the absolute value of 1, you get 1. When you take the absolute value of -1, you get 1. So regardless of n, the absolute value of -1 to the n is just 1. Suppose this series were to converge. If sigma n equals 2 to infinity 1 over the natural log of n converges, what would we say? Would we say that this series is absolutely convergent, or would we say that the original series is conditionally convergent? I'll say it one more time. Suppose this series, sigma n equal 2 to infinity 1 over natural log of n, were to converge. What would that tell me about the original series? Would it tell me the original series is absolutely convergent? Or would it tell me that the original series is conditionally convergent? Maggie's correct. If this series were to converge, then we would say that the original series, S, is absolutely convergent. Because when we replaced the inside by its absolute value, we got something that still converged. What if this series were to diverge? Then that would mean that the original series S is conditionally convergent, because we've already shown that S converges. Can't possibly be divergent. But if the corresponding absolute value series is divergent, that's precisely what it means to say that S is conditionally convergent. Convergent, but not absolutely convergent. Now the suggestion here is to try TFD on this series. We can do that. TFD says, if the limit of the ANs is not 0, then the series diverges. Well, here the limit of the ANs is lim n to infinity 1 over the natural log of n, which is 1 over infinity, which is 0. So what do we learn from this? Yeah, not a goddamn thing, unfortunately. TFD says if the limit of the ANs is not 0, then the series sigma AN diverges. But if the limit of the ANs is 0, then that's inconclusive. No, don't apologize. You're fine. This happens all the time. You know, we try something, especially the easiest thing, right? TFD is kind of the easiest thing to try. It just didn't happen to give us what we needed this time. Are there any other suggestions for what we could try? We could go for an integral test here. Integrating 1 over the natural log of x is challenging, to say the least. Like 1 over n natural log n, that's a more manageable integral test thing. But if you haven't tried integrating 1 over the natural log of x on its own, I encourage you to give it a shot. If you make any progress on it, let me know, because I have several research mathematicians who would love to hear the result. This fucking pen. But this is a hard integral. That's a natural log of x down there. I'm not saying that the integral is totally unmanageable. You can show that this integral does something, but actually calculating that integral, calculating an antiderivative there is very hard. Limit comparison might be too big of a hammer. What would we limit compare against? I do think it's manageable. It could be done with a limit comparison. What would you like to limit compare against, Zach? I can think of one way to do this with limit comparison. It's not super easy to think of something that grows at the same speed as the natural log of n. Yeah. So what's our gut feeling? Do we think 1 over the natural log of n summed from 2 to infinity? I'd love to just take a vote here. Give me a thumbs up react if you think that this series is most likely to converge. Guesses are fine. So we got a couple folks. Oh, a few folks, okay. And then a thumbs up if we think this series is most likely to diverge. Okay, so Maggie and Colin, what's your intuition? Why do you think this series might diverge? You're right, by the way. Good. Kind of reminds you of 1 over n. In particular, you know that the natural log of n is a little bit smaller than n itself, right? Let me talk to Desmos for a minute. The natural log of x is smaller than x itself, always. Blue is natural log of x. Red is just x itself. So the fastest move here is a direct comparison. And a limit comparison would work also, right? So the limit comparison against sigma 1 over n, that would work. But it would require at least 1 run of L'Hopital's rule, which is a little bit messier than is necessary. So the way I would begin here is by saying we can observe that the natural log of n is smaller than n itself, which implies that 1 over n is smaller than 1 over the natural log of n. Bigger denominator, smaller overall, right? Or if the denominator of 1 over log n is smaller, then it will be bigger overall than 1 over n. And for n greater than or equal to 2, we have 0 is less than or equal to 1 over n is less than, it's actually strictly less than, but 1 over the natural log of n, which is precisely the kind of inequality I need to get the divergence result from direct comparison test. I'll call this inequality star. Also, we know that sigma n from 2 to infinity 1 over n is a divergent p-series. P here is equal to 1, which is not bigger than 1. Thus, by the inequality star and the direct comparison test, it follows that sigma n from 2 to infinity 1 over the natural log of n diverges. This tells us this, together with our AST work, tells us that the original series S equals sigma n from 2 to infinity negative 1 to the n over natural log n converges conditionally. The original series definitely converges. That's what AST told us. But when we took absolute values inside the series, the result was a divergent series. So while S converges, it doesn't converge absolutely, which means it must converge conditionally. In other words, this is one of those dangerous series where I could get in and reorder the terms and fuck shit up pretty bad. I could reorder the terms and split it into two series, both of which are divergent. I could reorder the terms and change the value of the series while keeping it convergent. All sorts of nasty things. Do we feel like we understand the concept of absolute and conditional convergence? I'd like to say one more thing before I leave this topic to show you our final two tests. And that is that this theorem, oh shit, where did it go? God damn it. This theorem is sometimes very useful. And by that I mean, sometimes the easiest way to show that something converges is to show that it converges absolutely. Because the tests that we learned at the beginning of this section, at the beginning of this chapter, only apply to series with positive terms, one of the ways to go from a series that you can't do anything about to a series that you can learn about is by taking absolute values inside. So I'd like to do one last example, and I'll do it quickly before we talk about the root and ratio tests. This may push us on time a little bit, I apologize. Let's investigate the convergence of the series S equals sigma n from whatever, 1 to infinity sine of n over n squared. I'll tell you right now, this series converges. But showing the convergence is a tricky biscuit because it is not a series of positive terms and it's not an alternating series. The sign of n is sometimes positive and sometimes negative. But it doesn't flip back and forth from positive to negative every other term like an alternating series does. The sign of 1 is positive. 1 is pretty close to pi over 3. The sign of 2 is positive. 2 is pretty close to like 2 pi over 3, thereabouts. The sign of 3 is still positive because 3 is a little bit smaller than pi, but the sign of 4 is negative. The sign of 5 is negative. The sign of 6 is negative. The sign of 7 is negative, but the sign of 8 is positive again. So the top changes sign roughly every 4 values of n, but it's not even that clean because n is integer and pi is irrational, so it's not even that nice. This has some terms positive and some terms negative. But is not alternating. And that makes this a very challenging series to work with because our tests, the only shit we've got is tests that require everything to be positive, like the comparison test, the integral test, and the alternating series test, which requires every other term to flip. And this doesn't do any of those. So following what I said just a second ago before writing down this example, the easiest way to attack series like these is to look at the related absolute value series. again, we can split the absolute value up. Oh shit, I just realized I forgot to take out the recycling last night. I can hear them collecting it. Don't you hate that? All right. If you split the absolute values up, the bottom is always positive. It's a square for one, but also n is positive. So of course n squared is positive. And the top is bounded. So I can apply dct to the absolute value series here. Zero is certainly less than or equal to the sine of n in absolute value. And that is less than or equal to 1. All right, sine itself is always bounded between -1 and 1. So the absolute value of sine is bounded between 0 and 1. This implies if you divide everywhere by n squared, and since sigma 1 over n squared summed from wherever 1 to infinity is a convergent p-series, it follows from star and dct that sigma n from 1 to infinity absolute values sine n over n squared converges. Hence, come on. Hence the original series converges absolutely. So sometimes if you have a series that's tough to work with, one way to make life easier is to take absolute values on the inside. Now, if doing that gave me a divergent series, I wouldn't learn anything. All I would learn is that the original series doesn't converge absolutely. But in this case, when we took the absolute value on the inside, the result was a series that I could show converges using dct, which means that my original series converged absolutely. So here's a case where you're able to get a series that you couldn't work with into a form that you can work with by asking the absolute convergence question instead of the regular convergence question. And this is one of the ways in which that theorem is very useful. This maybe reminds you a little bit of that theorem we had on sequences that said, you know, an goes to 0 if and only if the absolute value of an goes to 0. So if you had a sequence tending to 0, but taking the limit was a little bit hard, you could slap absolute values on it and make it easier to work with. Same sort of thing. Okay, I do apologize, but I have to continue moving here because we have 2 more theorems to discuss today. This next theorem is called the root test. It says, let S be sigma an summed from wherever, I'll say summed from 1 to infinity. And let L be the limit as n goes to infinity of the nth root of the absolute value of an. If L is less than 1, then S converges absolutely. If L is bigger than 1, then S diverges. And if L is equal to 1, the test is inconclusive. The proof here is not terribly hard. I'll sketch it for you really quick. If L is the limit as n goes to infinity, nth root of the absolute value of an, then for large n, L is approximately equal to the nth root of the absolute value of an, which means L to the n is approximately the absolute value of an. So, if this number L is the limit as n goes to infinity of the nth root of an, what that means is as n gets bigger and bigger and bigger, this thing gets closer and closer and closer to L. That's what the limit means. In other words, if n is real, real big, this thing is real, real close to L. All right, well now raise both sides to the nth power. The nth power will kill the nth root, and you get L to the n is approximately equal to the absolute value of an. And now, if you sum on both sides from 1 or wherever, you get that these things are about the same. And the series on the left is geometric. So if the absolute value of L is less than 1, the series converges. Now, by how L is defined, it's not possible for L to be negative. So saying the absolute value of L is less than 1 is the same as saying L is less than 1. And if L is bigger than 1, the series diverges. All right, and I'll leave it at that as a proof sketch here. It doesn't need to be super rigorous or super detailed, and showing that when L is 1, the test is inconclusive is different. We can show that by example. But I just want to give you a feel for why the root test works. The root test is one of these tests that actually makes really good sense, kind of like the direct comparison test, whereas the other tests are a little bit harder to understand. The root test works because the number L that you calculate is the closest thing to a common ratio for a non-geometric series as you can get. That's the way to think of it. If you apply the root test to a geometric series, L will come out to the common ratio. If you apply the root test to a non-geometric series, then L will come out to the closest concept to a common ratio for that series. So if it is small, if L is small, then the series will converge, and in fact, the convergence is absolute. It's a super powerful test, because not only does it tell us that the series converges, it tells us that the series converges absolutely, which is nice. I'll give you just another second to write, and then I'm going to show you the ratio test, and then we'll do a couple of examples. Two more seconds. Okay. The ratio test is similar looking. Again, let S be sigma an, summed from wherever, 1 to infinity, 0 to infinity, 5 to infinity. The starting index does not matter. And let L this time be the limit as n goes to infinity of the absolute value of an plus 1 over an. So L here is the limit of 2 consecutive terms of your series. Same output here. If L is less than 1, then S converges absolutely. If L is bigger than 1, then S diverges. And if L is equal to 1, the test is inconclusive. Unfortunately, there's a shitload of really important series on which both of these tests are totally useless. If an is a rational function of n, both the root test and ratio test are inconclusive. In other words, if your series is a p-series or looks anything like a p-series, you're not going to get anywhere with the root or ratio test. Those just don't converge or diverge fast enough to be detected by the root or ratio test. Even if p is really large, they just don't work. The root test and ratio test are looking for more exaggerated, more aggressive behavior. However, there's a bunch of stuff on which they do work really well. And I would like to emphasize that these tests do not require the series to have positive terms. So the series I just wrote down here, sigma n from 0 to infinity, negative 1 to the n over n factorial. This is an alternating series. And until today, the only tool we had to work with this was the alternating series test. But the alternating series test kind of sucks. It kind of sucks because it'll never tell you that a series converges absolutely, and it'll never tell you that a series diverges. The alternating series test is kind of weak in a sense. It's only ever able to tell you that a series converges. And then you have to do more work if you want to figure out if that convergence is absolute or conditional. So rather than using the alternating series test on this, I'm going to use the ratio test. And another note here, anytime you see factorials or factorial-like things, in a series, try the ratio test. Because ratios of factorials cancel beautifully. We've seen that before. right? If you divide one factorial by another factorial, usually there's a shitload of cancellation because there's a lot of common numbers between any two factorials because they all multiply all the way down to 1. So let's do it. I'm going to run the ratio test. So we tell our reader, just like we always do before using one of these tests, we write down the name of the test we're using. And then we write down the recipe. This says L should be the limit as n goes to infinity, the absolute value of a sub n plus 1 divided by a sub n. In this case, that is the limit as n goes to infinity of the absolute value of -1 to the n plus 1 over n plus 1 factorial. That's an plus 1. You take an, and everywhere there's an n, you replace it by n plus 1, and you should do so in parentheses. Very common mistake is to not use parentheses when writing down an plus 1. Now upstairs here in the power, it's a little bit redundant, but downstairs here, it's very important that this is n plus 1 all factorial. It's not the same as n factorial plus 1. So this is an plus 1, and I need to divide it by an, which is -1 to the n over n factorial. And now I can close my absolute values. I'm dividing one fraction by another fraction, so I can flip and multiply. And I get -1 to the n plus 1 over parentheses n plus 1 factorial times n factorial over -1 to the n. And then I can sort of regroup my terms. Everything here is being multiplied. Fractions multiply straight across and in whatever order you want. So I can think of this as n factorial over n plus 1 factorial times -1 to the n plus 1 over -1 to the n. And I can split up the absolute values. Absolute values play nice with multiplication. Now the second piece right here, -1 to the n plus 1 over -1 to the n, that's just -1. And the first piece is positive, n factorial over n plus 1 factorial. So this is n factorial over n plus 1 factorial with no absolute values because this stuff is positive, times the absolute value of -1 to the n plus 1 divided by -1 to the n is just -1 to the 1. Now the absolute value of -1 is 1. So this piece goes away. I'm just multiplying by 1. So this is the same as the limit as n goes to infinity of n factorial, which is n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1 over n plus 1 factorial, which is n plus 1 times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. And you can see the massive cancellation here. The n's cancel, the n minus 1's cancel, the n minus 2's cancel, everything cancels except for the n plus 1 downstairs. So you get lim n to infinity 1 over n plus 1, which is 0. Therefore, the series S not only converges, but converges absolutely by the ratio test. So the ratio test is your friend. In fact, after exam 2, we're going to be talking a lot about power series. And in the context of power series, the ratio test is pretty much the only test we use. It's such a powerful tool. It works so well that it's what we use in general when talking with kind of bigger, harder to work with series. Questions on what we did here with the ratio test? Take your time, make sure you get this all on your notes. I'll give you a minute here. There's a lot of algebra stuff that we haven't necessarily practiced with very much. Algebra of absolute values. You have to remember your rules for exponents to simplify this thing. Does everybody know what I did to get from here to here? I subtracted the powers, right? Because I'm dividing like bases. The rule I'm using is that b to the x over b to the y is b to the x minus y. The other place where I've seen people struggle is with the factorial canceling. So upstairs, I wrote out n factorial here. N factorial is n times all the positive integers less than n. So it's n times n minus 1 times n minus 2 all the way down to 1. And n plus 1 factorial is the product of all the positive integers less than or equal to n plus 1. So that's n plus 1 times n minus 1 times n minus 2 all the way down to 1. When you're in a situation where you need to clean up a ratio of factorials, the safe path is always to write them out. Just use the definition to write them out. There are a lot of kind of fun, challenging examples that can be resolved with the ratio test and can't be resolved any other way. But I'll save those extra challenging ones for Friday when we review. Before we go, I would like to show you a root test example. Let's see, what should we do? So the root test is useful when you've got a bunch of stuff raised to the n. If that stuff that's being raised to the n is constant, then you're dealing with a geometric series. But if the stuff that's being raised to the n isn't constant, then you're dealing with a series that you should apply the root test to. So kind of a similar note. If your series looks like sigma stuff to the n, where the stuff is not constant, try the root test. In this case, if I run the root test, L is the limit as n goes to infinity of the nth root of the absolute value of an, that is the limit as n goes to infinity of the nth root of the absolute value of 1 over n to the n. Now 1 over n to the n is positive, so this is the same as the limit as n goes to infinity of the nth root of just good old-fashioned 1 over n to the n. And we can think of that as the nth root of 1 over the nth root of n to the n. And the nth root and the nth power here cancel. Upstairs, all the nth roots of 1 are 1, and downstairs, the nth root of n to the n is n. And the limit as n goes to infinity of 1 over n, that's 1 over infinity, which is 0. So since L equals 0 is less than 1, the series S converges absolutely by the root test. And that's job done. The root test is fun. Again, you mostly want to apply it when your series looks like a bunch of non-constant stuff raised to the nth power. If you can rewrite or think of your series in that way, then the root test is a good idea. Your textbook has a lot of good examples, and I'll be posting your study guide in just a few minutes with plenty of those examples picked out. But you want to solve as many problems as you possibly can in preparation for this test. I've said it a few times, but I'll say it once more. Exam 2, this content is the reason why this class has the reputation it does. I'm fielding questions through email and Canvas as rapidly as I can. I didn't see anybody in office hours yesterday, but I did have a few people in office hours Monday. If you want to talk, please talk to me. Do not struggle through this stuff on your own. Make sure you're talking to your classmates, peers, tutors. There is one tutor in the Learning Commons who is exceptional with this stuff, and his name is Alejandro. You can get hooked up with a tutor by following the link on our Canvas page, or by going to the Learning Commons Canvas page on your own. But make sure that you're bouncing your ideas and your solutions off of other people. Don't just be writing these out and trusting that everything is perfect, because I promise you it's not. If you show your shit to somebody else, they're far more likely to spot little issues in logic or algebra than you are. It's just the nature of being human, is that we don't spot our own mistakes because there are mistakes. We made them in the first place, but other people often can. So share your solutions with each other, share them with me, share them with tutors. Make sure that you're checking your work in a way that is rigorous. I know that no matter what I put in WebAssign, it won't be sufficient to prepare you, because you can just click the button that says converge or click the button that says diverge, and if you get it wrong the first time, you can switch it. WebAssign says that each of these problems should take like 2 minutes, which is bullshit. It says that because people just guess one, and if it doesn't work, they guess the other, and the aggregate statistics show that it's done quickly. But I know the truth here is that if you're actually writing out these problems and doing the solutions, they take longer. So please make sure that you're sinking appropriate amounts of time into this, and appropriate amounts of time are like at least 3 hours a day. At least 3 hours a week outside of class if you're not behind. If you have fallen behind and you're still working on any of the older material sequences or any of the stuff from last week, then you need to be sinking considerably more time in something like 8-9 hours a week. Don't try to squish all that in over the weekend. You'll have a shitty weekend and it won't work. But even if you're behind, even if you're still back in section 11.1, there's still time to catch up. But you need to start dumping time in today and every day between now and the test. All right, if you would like help with anything, you know where to find me. I'll be in my office hours, or you can Canvas message me if you want to set up an extra office hour. Feel free to do so. I will be on campus this Thursday, tomorrow at 9:45 a.m. in my office, A031D, or somewhere nearby there, because I'm working with a student from another class. If you want to talk to me in person, you want to talk to me through Zoom, any of those things, please do. One note is that tomorrow, Thursday, I will not have my normal online office hour. I'm doing the in-person office hour at 9:45, and then I'm going to go vote early, which will get in the way of my normal office hour. But I'll try to conduct an office hour when I get home. That will depend on how long the lines to vote are. So if I'm in line for 3 hours, the online office hour might end up being later in the day, like 3 or 4 p.m. If we're able to get in and out quickly, then I might be able to do the online office hour as early as like 1. But I'll post an announcement letting you guys know exactly when it will be. Just be aware that while I do have my normal online office hour today, and I do have an in-person office hour tomorrow at 9:45, my online office hour tomorrow will not be at its normal time. It will be later. And unfortunately, I can't tell you exactly when because it depends on how long the voting lines are, but there will be an announcement. All right, I got to get running. I got another class to start. I hope you guys have a lovely rest of your day. Please be working hard. And if you are uncertain about anything, please communicate it to me. That is all. Take care, guys.